Hi, my name is Nina, and for assignment 3, I decided to create an AI behavior tree which helps make decisions for my animal non-playable characters, whom are currently colourful blocks, hopefully to become animals in the near future. I have always found NPC behavior in games to be really interesting, and I always wondered how they sort of had brains of their own and how this could be implemented in code. I've used really simple finite state machines in the past and thought that it would be interesting to try a behavior tree because of its reputation for being easily extendable and easy to implement. My targeted design quality is utility because I definitely think that I'll be able to use the behavior tree system in future projects, and that I'll hopefully be able to take some of my components and leaves created in this project in the future. So this was my core plan for the behavior tree code structure. All of the possible nodes of the tree inherit from the behavior node class, which enforces the fact that each of these nodes must have a use function, which will always return an eBehavior status. The eBehavior status contains 3 different statuses, such as failure, success, or running. If it returns a success, that means that this node has finished running and that it's complete, and that basically the behavior tree can move on to the next node in the sequence, or that the behavior tree can move on to a different branch or a different leaf, and so on, really depending on the composite node above it. And if it returns a failure, that means that this node has failed, which will also change the behavior of the tree. And if it's running, that means that this node will continue going. Non-leaf nodes inherit from the composite node class, which has a variable which is a t-array of behavior node pointers called children, which will be used in their use functions, and it will differentiate depending on the type of node. So for example, the sequence node class will iterate through the list of children and call the use functions of these children. If the child returns an eBehavior status failure, the sequence node will return a failure. If all of the children run correctly, or return success, the sequence node will return success. The selected node's use function will iterate through all children and return success if any one of the children returns success. If none of the children return success, then the selected node will return failure, and the inverter node will return the inverse of its child node. Composite nodes also have a function called addChild, which returns nothing and accepts an argument of a behavior node pointer, which is the child that will get added to the list of children. Leaf node uses delegates to run functions attached to them. So I have made a variable called event, which I will allow developers to bind a function to this event, which will be called in the use function whenever this leaf node is used. For example, this is me binding a carnivore check to a leaf node, and this allows me to basically attach this function into my tree, and I'll be able to reuse this leaf wherever I want. In the delegate for these leaf nodes, they must have a return type of eBehavior status, and that's the only condition for this function. They just must return an eBehavior status, which will allow them to be used in the behavior tree. This is my behavior tree that I've recreated in code using my structures from the previous sections of this video. I found it easier to lay out all of this logic in a tree visually before I went in and programmed it, because it made it much easier for me to read and debug, to make sure that I didn't skip over any sequence nodes or selected nodes or anything like that. The main behaviors that this NPC animal has currently are to walk to random nodes, to run away from other animals, which occurs when the animal has low health, and to eat. The eating behavior is different for each different type of animal. Herbivores will go to the closest food node to eat, denoted by the green color of the node in this demo. Carnivores will go towards the closest animal and attack them until the animal dies, then they'll be able to eat them. And then omnivores can either eat a plant or eat an animal. This is dependent on whether there are any animals nearby. Omnivores will prioritize eating an animal before eating a plant. As you can see in the code, there are certain segments of the behavior tree that I was able to reuse. For example, I reused the carnivore and herbivore logic in the omnivore branch of the tree. This was simple to do because I could use a composite node which can store pointers to child nodes, and because I had pointers to the carnivore and herbivore logic earlier on in my code, I could easily add these pointers to the composite omnivore selector node. I also reused many of the leaf nodes throughout my tree. This helped to condense and simplify the code, and this will make it easier for me to debug in the future. Some other additional AI behavior that I added to support my behavior tree was to add decaying health and hunger components, which has added functionality to some of the code from the weekly labs. I added values to each of these classes that specify the rate of decay, and then in each tick, the hunger and health values will reduce by that rate. Currently, this rate is the same across all animals, but ideally in the later tech demo, this may become procedurally generated. Okay, so now for the part that we've all been waiting for, the tech demo. So here, as you can see, I've got a square of a bunch of navigation nodes, but as you can see here, there are some nodes that are green, and these are our food nodes for the herbivore and omnivores. Here I've got my 3 different animals. This is a herbivore, this is a carnivore, and this is an omnivore. So here, when I hit play, you'll see that they're moving around in random directions, doing their normal roam behavior. Sometimes they get a bit stuck, but that's okay because eventually they'll move away from each other. And yeah, so over time their hunger is decaying. You can't see it right now, but you'll notice their behavior change as soon as they get hungry, which you'll see in a console log any minute now. Maybe a couple years later. As you can see, they've got some stats here. I've got my carnivore. The carnivore can do 30 damage, so like 30 of a health value, and they have an attack cooldown of 5. And you can see that their current path is changing and that they have sensed animals. As you can see, one of the animals is just eaten. This would be the herbivore animal. Yes, this is a very long and complicated name, I know. But as you can see, oh, and now one of them's low. I think that's the herbivore. The herbivore is low, so you can see that the herbivore is trying to run away from all of these animals. So doing the flee behavior. Another animal has just become low. I think that's the carnivore, because they're also trying to run away. It's a bit confusing, the flee behavior, because it relies on the closest animal. But you can sort of see them trying to get away from this omnivore right now. Both of them. And this will go on for a very long time until one dies. There we go, the carnivore has just died. And the omnivore has just eaten, and you can see that their hunger value has changed. And now the omnivore is going to continue chasing this herbivore. So now the herbivore is going to try to escape the omnivore, doing the flee behavior. This will go for a while because it's just going to keep going around this edge of the square. Nope, the herbivore also just ate, I think. I think that was. Kind of lost it in the sea of low health now. And there we go, the omnivore has eaten the herbivore, and now the omnivore just ate from a plant node as well. And that is the demo. I'm also going to show off what it's like when you've only got a couple of these, so I'm going to get rid of both the carnivore and the omnivore to show off just the herbivore's behavior. So as you can see, normal roaming, and then eventually it'll eat a plant. So any day now. There we go. The herbivore has just eaten, and as you can see, the hunger was below 50, which is the condition for the hungry sort of stat, and now it's gone up by 30 to 79. I'm also going to show off the omnivore. So the omnivore can either eat, like attack an animal to eat, or eat just from a food node. I'm going to show you that it can just eat from a food node. Maybe I should have put down herbivore to show off, but I think that you saw the omnivore already attacking, so that should be fine. And there we go, the omnivore has eaten at a plant node. And finally, I'm going to show off both a carnivore and a herbivore together to show off the carnivore's behavior. I'm gonna put down a new animal. Here we go. Now we've got a carnivore, and oh, that's also a carnivore. Let me make this herbivore. Let me move this under here. Herbivore. Gotta make sure that the carnivore can actually do damage, or else then that's gonna be an awful test. And okay, there we go. So carnivores can only eat animals, so that means that once this carnivore eats this herbivore, it will not be able to eat anymore. And at this point in time, the animals will not die when their hunger reaches 0, but I think in the final tech demo, they will die. So there we go, the herbivore has just eaten. And the carnivore is currently chasing the herbivore, as you can see, which means that the carnivore is hungry. So now the herbivore is low. It's trying to run away. Carnivore's still attacking. And there we go. The carnivore has eaten. As you can see, the carnivore's still hungry, but as you can see, it's not getting a path to any of these food nodes. It's just hungry, and it's just going to stay hungry. And yeah, that's the whole tech demo. For assignment 4, my group member and I plan to have these animals roaming on a procedurally generated landscape, and for these animals to have procedurally generated stats. We would also love to have character models for these animals. Unfortunately, red, orange, and green cubes are not ideal. We also plan on implementing multiplayer so that each of these stats and animals are replicated from a server onto multiple clients, so that each player has the same view of the animals. We would also like to allow players to spawn in more animals during the demo, but have some concerns about needing to optimize some of this code for the AI behavior and pathfinding to reduce lag. We also plan on having visual indicators for animal health and hunger, rather than relying on console output to know when an animal is low and when an animal is hungry and has eaten. I think that both me and my group members' projects will work together well in assignment 4 because my group member will provide procedural generation, which will help alter the way that the behavior tree works for each of the animals. So, for example, providing different landscapes, different stats, different types of animals generated and stuff like that. So I think that it will be okay to put together later. We'll see. We'll really see. Thank you so much for listening to me talk about my behavior tree system, and I hope that you enjoyed the crappy tech demo and the lovely, lovely graphs of my behavior tree.